In section 4.4, we want to continue our discussion of irreducible and reducible polynomials in f of x, where f is a field. Remember what we've discussed so far. What did it mean for a polynomial, little f and big fx, to be irreducible? That means if you could write little f of x as a product of two other polynomials, one of the two polynomials had to be a constant. Okay, so how do you show a polynomial is irreducible? Assume little f of x is little g of x times little h of x. Show that either g or h has to be a constant, which means the other one is an associate. The other factor would have to be an associate of f. Now, we had one example, we did one theorem where we knew that polynomials of degree 1 in big f of x were irreducible. So we proved that. So you have a collection of examples you can already draw from. And then we had another theorem, how do you get a polynomial is reducible? So how do you show little f of x is reducible? You write it as g of x times h of x, where g and h both have degrees strictly less than the degree of f. So that's all we have so far. So this section we want to continue with how do we get polynomials are reducible. And we, throughout the section, capital R denotes a commutative ring. We're going to quickly switch to a field anyway, so f throughout the section will be a field as usual. Well, first we have a definition. So suppose you have a polynomial that we've been doing a sub n x to the n plus a n sub 1 x to the n minus 1 plus dot 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 plus a1x plus a naught in Rx. So R is our commutative ring, and the a sub n through a naught, those are all the coefficients from R. So we already know what the polynomial looks like. Now take this polynomial, and instead of thinking of it as a polynomial in Rx, think of it as a function from your ring to your ring. And we're going to define it by f of R. Well, just plug R in for x. So that's all we're doing here. So notice if I plug R in for x, R to the nth power is going to be another element of R, times a sub n is another element of R, because R is a ring. So if you continue this down, all these products and sums will wind up being an element back in R. So you plug in an element of R for x, and it spits out an element of R. So it is a function from R to R. Okay, so that's called a polynomial function because it comes from a polynomial. And I added in the notes, you'll see, induced by the polynomial p. So this is the function induced by the polynomial p. So the next example says, consider the two polynomials x cubed plus x squared plus 1 in z2x, and x cubed plus x plus 1 also in z2x. Now, I didn't write those down as polynomials. I've written them down as functions. So think of f as a function from z2 to z2. So if you plug in an element in z2, it'll spit out an element in z2. Same for g. So the problem says, show that these two functions are the same function. Now, how do you show two functions are the same? Well, you show that no matter what you plug in for x here, if you plug the same thing over here, you get the same answer. Okay? So there's only two things to check. So pause the video and see if you can show little f and little g are the same thing as functions. Okay, so let's actually compute. So let's find f of 0. Well, f of 0 is 0 cubed plus 0 squared plus 1, which is 1. And let's find f of 1. Well, that's 1 cubed plus 1 squared plus 1. Now remember, we're working inside z2, so 1 plus 1 plus 1 is 3, but 3 mod 2 is 1. Now what if we do the same thing over here? G of 0 is 0 cubed plus 0 plus 1, which is 1. And then g of 1 is 1 cubed plus 1 plus 1, which again is 3, and we're in z2. 3 mod 2 is 1. So notice f and g do the same thing to 0. They take 0 to the same element 1. They take 1 to the same element 1. So our conclusion is f is g. Now what's the point of this example? These two polynomials in z2x are different polynomials. This is x cubed plus x squared plus 1. This is x cubed plus x plus 1. As polynomials, we think of them as being two different things. But as functions from z2 to z2, they're the same thing. So the point of the example is two different polynomials in Rx, right, in our ring Rx, can induce the exact same function. Okay? So that's something to keep in mind. You have to know, are you thinking them as polynomials, which means they're different, or are you thinking of them as functions, which in this example means they're exactly the same. So the next example is an exercise, and we've done examples similar to this before. I think when we're doing groups, if I remember correctly. So this is number 24, and it says, let A be a fixed element of F, okay? So we can pick any element we want in the field F, and once you pick it, you're sticking to it. And we're defining a map, phi sub A, which is mapping from the ring of polynomials to the elements of F. So this mapping, the domain are polynomials, and the codomain are elements of F in the field. And the definition is phi of A of a polynomial. Now I'm writing F, I'm not thinking of it as a function, I'm thinking of it as a polynomial, is F of A. Now does that make sense in terms of the domain and codomain? So if I take a polynomial in Fx, and what does the rule say to do? So phi sub A of F of X is F of A. Well, A is an element of F, and when you plug that into F here, F of A is going to give you an element of F. Okay? So notice here I'm thinking of this as a polynomial, but as soon as I write the F over here now, F of A, I'm plugging something in, I'm thinking F as a function. So I'm using F two different ways here. Here, F is a polynomial in F of X. This F, I'm thinking of it as the function induced by the polynomial over here. But we are taking polynomials and mapping them to elements of F. And the instructions say, prove that phi sub A is a surjective homomorphism of rings, and the map phi of A is called an evaluation homomorphism. And notice, for every element of A, there's an evaluation homomorphism. So this is a quick way to construct homomorphisms from Fx to F. So we want to show this is a surjective homomorphism. Okay, so what do we have to show? We have to show the linearity property for addition, for multiplication, and then we have to show surjectivity. Okay, so we have to show the linearity, so let's let f of x and g of x be in big Fx in the ring. Then phi sub A of f of x plus g of x. Well, what's the definition of the sum of two functions? That's f plus g of x. That's the definition of f plus g of x, is just the sum. And now, what's phi sub A of one function? The reason why I wrote it that way is it says, how do you take phi sub A of a single function? So instead of thinking this as two functions, I'm thinking of it as one. Well, the definition of phi sub A says that's f plus g of A. But again, what's the definition of the sum of two functions? F plus g of A is f of A plus g of A. But what's f of A? That's phi sub A of f of x plus phi sub A of g of x. So I have phi sub A of the sum is the sum of the phi sub A's. So there's the linearity property for addition. I'm going to erase up here and continue. Okay, so I'm continuing on here. Also, we have to do this for multiplication. Phi A of f of x, g of x. Well, I'm going to do the exact same thing pretty much I did here. What's the definition of the product of two functions? That's fg of x. Notice this isn't composition, this is multiplication. I didn't put the circle there to indicate composition. That means multiplication. Well, what's the definition of phi sub A? That's fg of A, but fg of A, by definition of the product of functions, is f of A times g of A, which is phi A of f of x times phi A of g of x. So these two parts together, hence phi sub A is a ring homomorphism. Okay, So those two parts give us our homomorphism. So the only thing left to do is show surjectivity. So we need to show that the phi sub a is onto. Right? Now, so let me write again what we have here. Phi sub a is mapping f of x to f. Okay, so what's my thinking here? How do you show a function is onto? This has nothing to do with ring theory. This is just going back to when you had your first discrete math course. So what do? You pick an element in the codomain and you find something in the domain that maps to it under phi. Okay, under phi sub a. Okay, so you start with something arbitrary in here, find a polynomial that will map to it. Well, let me just do some scratch work here. So let me pick something over here in f, say c. Okay, I'm just picking c, just pick something, c for constant. Now I need to find a polynomial over here, say f of x, where phi sub a of f of x gives me that c. Well, what's phi a of f of x? That's f of a. So I need to make up a polynomial in f of x that will map that a, whatever that a is, to the c that I've chosen over here. Well, can you come up with a polynomial that does that? So when you take f of a, you have to spit out the value c, no matter what you pick for the c here. Well, it seems like the easiest thing to pick is the constant function. Let's choose f of x as c. Just, right, that constant polynomials are in f of x. Remember, elements of f are in fx. So that should work. Is that the only thing that works? Probably not. What if I did f of x is, can I make a linear function that does that? I need the answer to be c, and I want to plug in a, I have to get c. So what if I did x minus a plus c? Right, so minus a plus c is a constant, that's an f. And so if I take f of a, I'd have a minus a plus c is c. So you could make up a linear function that would work here too. But we don't need to make it that complicated. Okay, so let's write up the surjectivity proof. So let C be an F and consider, again, I use the word consider in a proof to indicate that I'm pulling something seemingly out of thin air. Consider f of x in fx given by f of x equals c. So I'm telling the reader what element I'm choosing in here. Then we just have to show that phi a of the f I've chosen gives me the c, but we know it's going to work. Phi a of this f of x, by definition of phi sub a, that's f of a, but we just said f of anything is c. Thus, my function phi sub a is surjective. So to end, we conclude that phi sub a is a surjective ring homomorphism. Okay, so there's my proof. Okay, that wasn't too bad. Okay, let's move on to the next definition. And this should not surprise you at all. So it's the exact same definition that you learned when you first did, algebra. Okay, it says pick a polynomial in R of x. So f of x is a polynomial in Rx. Then an element a in R is called a root of this polynomial if f of a is 0. That's the exact same definition you learned in college algebra, or algebra in your Algebra 1 course in high school. Now, you have to realize that roots, when we talked about this before with reducibility, roots depend upon the coefficient ring. So the example I give here is if you take x squared plus 1 in Cx, well, C is complex numbers, does this have a root? This is my f of x. Yes, it does, because f of I is I squared plus 1, which is minus 1 plus 1 is 0. So I is a root. But if you think of x squared plus 1 as being in the ring Rx, real number coefficients, there is no root, because the only two roots of this in C are plus or minus I, and neither of those are an R. Okay, so whether you have a root depends upon your coefficient ring. Okay, so the theorem here, we're heading towards relating roots and factors of polynomials, but first we have the remainder theorem. This is theorem 415. It says let f be a polynomial in f. Okay, so f of x is a big fx, and a is an element of f. Fine. It says the remainder when f of x is divided by x minus a is f of a. So if you have a polynomial and you divide by x minus a, so they're relating the root to another polynomial, the linear polynomial x minus a, the polynomial of degree 1. Well, what does the proof say? Again, it's all written out in your notes. I'm just going to put the highlights here so I can look at it. Well, remember we had the division algorithm says if you have a polynomial and you divide by another one, here we're dividing by the polynomial x minus a. So if we take f of x and divide by x minus a, you will get a polynomial here, I'm using q for the quotient, plus another polynomial that I'm using r for the remainder. Now what was the restriction on r? R is either equal to the 0 polynomial, so there's no remainder, or the degree of r is less than or the degree of the divisor. Okay, so notice, right, so if r of x is just 0, suppose the remainder were 0, well, r is a constant, right? Okay, now what if the degree of r were less than the degree of x minus a? That's the other possibility. But the degree of x minus a is 1. It's linear. Well, if the degree of r is strictly less than 1, that means the degree of r is 0, which means r is a constant. So if r of x is 0, r of x is a constant. If the degree of r of x is less than the degree of x minus a, r of x is a constant. So in either case, you get r of x as some constant. And so I said, suppose r of x is c, for some c. Well, what do you have? F of a, if I plug in a, I get a minus a, q of a, plus r of a. But that's 0, because a minus a is 0. And we just said r of a is some constant c. Okay, and so what's the remainder when f of x is divided by x of a? Well, it's f of a, because I said r of x was c, but that's the same thing as f of a. Okay, so if you ever want to know the remainder when you divide by this term of the form x minus a, just plug a into f, and whatever answer you get is going to be the remainder. Right? The remainder is obviously going to be constant. We proved that. If you divide f of x by x minus a, r of x is a constant. So you plug a into f of x, and that'll give you the value of the remainder. Okay. So the next theorem, 416, is called the factor theorem. So same situation, you pick a polynomial f of x and an element little a in f. It says a is a root of f of x if and only if x minus a is a factor of f. So again, we're relating the element a to the polynomial x minus a. So a is a root if and only if x minus a is a factor. Again, this is true when you did college algebra. Okay, but we were working over the real numbers. So our field was the real numbers in that situation. Okay, so let's look at the proof here. It says, suppose we're going in the direct implication. Suppose a is a root of f. We want to show x minus a is a factor. Okay, so assume a is a root. Again, this is all written out in the notes. I'm just going to paraphrase here. So assume a is a root of f. Well, just so what would that mean? That means f of a is 0. That's a definition of a root. Well, we just discussed you can write f of x as x minus a times some q of x quotient plus some r of x. That's by the division algorithm again. But we just said in the previous result that r of x, the remainder, is the value when you plug a into f. So that's f of a, right? That's what we just proved, that the remainder when you divide by x minus a is f of a. But we said f of a was 0. Plus 0, so I'm not even going to write it. And notice what we have. X minus a times q of x is f of x, so x minus a is a factor of f, and that's what we were trying to show. So if a is a root, x minus a is a factor. So that's that direction. Now we want to go the other way around, the other direction. We want to do the converse. So now suppose x minus a is a factor of f of x. Well, what would that mean? That means f of x is x minus a times something else. Call it g. I'm not sure why. Okay, well, so if x minus a is a factor, that means x minus a times something is f of x. Well, what's f of a then? F of a is a minus a, g of a, but a minus a is 0. And notice a is a root because f of a is 0. So the proof is pretty straightforward. So a is a root if and only if x minus a is a factor. Now a corollary here says pick a non-zero polynomial in your ring fx, then f has at most n roots in f. Now I didn't write out all the gory details of the proof here. This is just the sketch. Okay, so it says, so find a root of f of x if you can. Okay, so we just said if you can find a root, say a sub 1, we just said that if a1's a root, x minus a1 is a factor. So you'd have that f of x is x minus a1 times something else. Well, now try to find a root of this polynomial that's remaining. Say you find root a2. Well, that means x minus a2 would be a root of whatever's left. And you keep doing this process. Whenever you factor, you keep finding roots until you factor it down to something of the form. Suppose you can get it down to x minus a sub n times some hn of x. So this n is just referring to how many roots we found. So notice I have a1, a2 through an. So assume I could factor f into, I found n roots here. So a1 through an are the roots. And they don't necessarily have to be distinct. A1 and A2 could be the same thing. I'm counting them, the multiplicity separately. Right? So I have n roots, and then I have times something else down here, whatever it is. Okay? So I'm saying whatever I have there, I don't know what it is. I'm just calling it h sub n of x. Okay. So, well, let's argue. Well, we know that n is the degree of f. Right, it says in originally f of x has degree n. That's stated in the hypothesis here. Okay, so the degree of f is n. Well, remember we had a theorem that said if you had a product of polynomials in fx, where f is a field, well, it's equal to the sum of these degrees. So that's the degree of x minus a1 plus the degree of x minus a2, etc., plus the degree of x minus a sub n, plus the degree of hn of x. Well, these are all linear up through here. So the degrees of each of these, that's 1 plus 1 plus 1 plus 1 plus 1, plus the degree of that unknown term. But how many of these are there? Well, there's n of them. I just said there were n roots here. So this is n plus the degree of hn. Well, what's the conclusion? N is n plus the degree of hn. So if you subtract n from both sides of that equation, you get the degree of hn is 0. Right? So hn is a constant, which doesn't have any roots. And so in this situation, f has exactly n roots. So if you can factor it as a product of n different linear terms times something else, that turns out to be a constant because the degree turned out to be 0. And so you have those n roots. Again, if a1 and a2 are the same, we're counting them as two different roots. I guess if you didn't count them as the same, it says it has at most n. So if you count them separately, there's exactly n, but if there were repeats, it would have less than or equal to n, so that's okay too. Okay, so that's the first situation. Now the second situation says, what if you do this instead? What if you go down and you factor, this is part 2, and you find k roots, and then you're left over with a k. So suppose you factored this down and you found k roots, and you have some extra polynomial that didn't have any more roots. Well, if you use the exact same argument here, n is the degree of f still, but notice here, that turns into a k, and that's my new polynomial k. And you have 1 plus 1 plus 1 plus 1 plus the degree of hk. But how many of these are there? Well, there are k of them now. I'm assuming we only found k factors, k linear factors. So we have k plus the degree of that. So what's the conclusion here? N is k plus the degree of this hk. So if I subtract k from both sides, I get n minus k is the degree of hk of x. But the degree of hk of x has to be bigger than or equal to 0, doesn't it? Right? Polynomials don't have negative degrees, so I know the degree of this is at least 0. But if n minus k is bigger than or equal to 0, what does that tell you? N is bigger than or equal to k, right? If I add k back to both sides. So n is bigger than or equal to k. So if you can factor f of x in this form with k roots here, with something left over, what did we just show? The degree of f, n, is bigger than or equal to k. So if there are k roots, n is bigger than or equal to that k, so there's at most n roots in f. So in either case, we get what we want. And again, for real numbers, you knew this was true, right? If you have a polynomial with coefficients from the real numbers, and your polynomial is of degree n, there are most n roots in the real numbers for that polynomial. So this result shouldn't surprise you. The next example says, consider the following polynomial. I'm not going to write this down. F of x is x to the 5th plus 2x to the 4th plus x cubed plus x squared plus 1 and z3x. Notice when you plug 1 into that polynomial, you get 1 plus 2 plus 1 plus 1 plus 1, which is 6, but 6 in z3 is 0. So f of 1 equals 0. So we have this polynomial, f of x in z3x. Let me read it again. It's x to the 5th plus 2x to the 4th plus x cubed plus x squared plus 1. When you plug in 1, I get 0. And from the theorem up above, notice 1 is a root of that polynomial, so x minus 1 is a factor. So this original polynomial f of x you can write as x minus 1 times something else. And notice f is reducible, because this has degree 1, that will have, this was a quintic, the degree of f was 5, that has degree 1, so g will have degree 4. So f is reducible, because I've written f as a product of two polynomials of lesser degree than 5. So using this idea, the next example says, suppose you have little f and big fx, and suppose the degree of f of x is at least 2. Then if f is irreducible, then f has no root in big F. Okay? So if f is irreducible, it won't have a root in f. Now, the way that's written isn't really the way we use this result. And we usually use the contrapositive for this. So if you write this as a contrapositive, if f has a root in f, then f is reducible. Notice that's the exact fact I used in the previous example. So typically you're trying to determine whether a polynomial is reducible or not. And so, here, if you know it's irreducible, then it doesn't have a root. That's not real useful because you typically don't know whether f is irreducible or not. The contrapositive is what we really use. If you can find a root in f, we know f is reducible. Okay? So again, these are equivalent statements because they're contrapositives of one another. Now, why this? Why did they assume the degree of f had to be at least 2? Why did they assume that? Well, if you take a polynomial of degree 1, suppose I put f of x is x minus, 2. Let's just put that in Rx, real numbers. Well, we learned before in fx, linear polynomials are irreducible. Right? So this is an irreducible polynomial from a result we had before. But it does have a root in Rx, x equals 2. Okay? So if you don't say the degree is at least 2, this isn't a true statement, right? Here, this polynomial is irreducible, but it does have a root. So if the degree of f is 1, the statement's not true, right? But it is true for anything bigger than 2. So this theorem tells you, how do you show a polynomial is reducible? Find a root. So as soon as you find one root, the polynomial is going to be reducible. Now we have to be careful here. Let me just leave the contrapositive I've written here. The converse of this is false. If f is reducible, well, let me go back to the original one. That's not what I want. Okay. Let me go back to the statement we had before. Right. So the way the corollary was written, if f is irreducible, that implied no root. Now what's the converse? So if f has no root in big F, then f is irreducible. Okay? This is not true. Okay? So you cannot use this result to show irreducible. You can only use the result to show reducibility. And the example I have here I say, look at the polynomial x to the 4th plus 2x squared plus 1, and let me write that. That's x squared plus 1 quantity squared. And I just said, consider this in the ring Qx. Q is the rational numbers. Notice this polynomial is reducible because I've written it as the product of two polynomials of lesser degree. But notice there is no root of this in Qx, because the roots are plus or minus I. So just because there's no root doesn't mean it's irreducible. This polynomial does not have a root in the field Q, but it's reducible. So this is not true, okay? So you cannot use this result to show irreducibility. Now, the good news is, this result is true for a polynomial of degree 2 or 3, and we'll continue that in the next video.